This research is a result of paper published in the Energy Journal with the same name as this presentation. And the main motivation behind this research is the fact that hydropower has not evolved for the last 100 years. If you see the Pelton turbine, Kaplan, Francis turbine, they have been their patents have been created around 100 years ago, and not much innovation has been created since for competitive hydropower solutions. So hydropower is a very inflexible electricity generation solution in regards of space. Of course, in regards of operation, is very flexible. You can increase and reduce operation electricity supply very quickly with the turbine and generator. But the space, the area available for harnessing electricity with hydropower is inflexible, and the capex, the investment costs, are very high for hydropower. And for hydropower is particularly interesting for has particular significant gains in scale. So the larger the project, the cheaper it becomes, and we wanted to find an alternative for this. And so we proposed electric truck hydropower, which consists of electric trucks with an empty container. This is, for example, one electric truck with one container, but the truck can pull, for example, 3 or 4 containers to increase the efficiency of the system. The idea is that the truck will go up the mountain empty and then replace its empty container by a container filled up with water. And then the weight of the truck would increase 70 to 80% with the water. And then the truck will drive down the mountain with regenerative braking, transforming the potential energy of water into electricity, which will charge the battery of the truck. Once the truck reaches the bottom of the mountain, the battery will be charged and then is replaced by a partially empty battery with enough charge for the trip up the mountain again. And then the cycle continues endlessly. So the advantage of one of the advantage of electric truck hydropower is that the truck can generate electricity at different locations. So the truck can move with, for example, a storm, and make use of as much as possible of the rain. It's flexible because if the truck is not being used for hydropower, it can be used for cargo transportation. Another interesting aspect is to combine cargo transportation with hydropower. So for example, if you are in Bolivia and you're delivering soybeans and you have to cross the Andes, you are fully loaded, you go up and down the mountain. But then when we're going back, when you are on the top of the mountain, you can fill up your truck with water and then recharge the battery of the truck on the way down. This is not only in a case for Bolivia. You have several other cases. For example, from Washington to Philadelphia, you have to cross a mountain. Several other locations where you need to cross mountains, and the return trip, the truck returns empty. You can generate electric truck hydropower. So of course, the advantage of having several containers for one truck is that the overall curb weight of the system reduces and the efficiency then increases. The ideal would be not to have the cabin have, for example, a truck on skates like it's shown in this figure, with in which the curb weight of the truck is significantly smaller. This is a very large battery. The electric truck hydropower wouldn't require such a large battery because the distances are rather small. So the methodology applied in this research, our first step is to find the efficiency of the system, considering the running resistance losses, the drag losses, and other losses in the system, motor, batteries, the generator cost estimation, the electricity generation cost estimation, data collection in order to find the world potential for electric truck hydropower, and then we estimate the global potential for electric truck hydropower. The main equation to estimate the amount of electricity generation is the potential energy, where the mass of water is multiplied by the height difference that the truck carries the water, the acceleration of gravity, the efficiency of the batteries to charge and discharge through a whole cycle, and the efficiency of the motors also to go up and down the mountain with the regenerative braking system also. And the losses, the main losses are the rolling resistance and the friction with air. The higher the velocity of the truck, the higher the losses. But of course, the higher the velocity of the truck, the more electricity generation you generate. So then you have a optimum point, which we have found and assumed to be around 40 kilometers per hour. So the data applied in the paper is the topography from SRTM, road infrastructure from GRIP, and runoff data from ECMWF. So these data were adjusted to have the same resolution, and then the methodology was developed in order to take into account. I'm not going to go too much in detail on the methodology. You can feel free to read the paper to learn more about the methodology. So this is the topographic data applied. This is the runoff data applied from ERA 5. ERA 5 is one of the projects from ECMWF. It presents very accurate, very good estimated data on runoff. We use runoff because we are talking about very small streams for electricity generation, so we are considering the runoff in these particular areas. And the road infrastructure we get from GRIP, which we are not proposing to build roads, so we are proposing to use existing roads. So of course we need a very good database for road infrastructure to estimate the global potential for the technology today. In order to find the slope applied, we use this equation. So we have the minimum theoretical slope, which is the average distance from one pixel to the other, and then we make an adjustment. Of course, roads are not straight, they have curves, and the road slope cannot practically exceed 15% of grade. The electric truck used in this paper was from Ningbo Berzon Haida Trading Corporation. I found their product in Alibaba, and the price is a competitive price, but the reason why I chose this truck is because they give a lot of details on the product, which is very rare, and these are very important in order to run the model and to estimate the losses and the energy generation, the costs of electricity generation. So the results show that the ideal velocity is 40 kilometers per hour in most of the slopes driven. So we assume 40 kilometers per hour, and we have the efficiency varying mainly with the road slope. So the most significant variation of the impact on the efficiency of electric truck hydropower is the road slope and then the speed of the truck. because the higher the speed, the higher the losses, the drag losses, and then the efficiency reduces significantly. So for example, with a slope of 10%, road slope of 10%, and a velocity of 40 kilometers per hour, we have something around 61-62% efficiency, overall efficiency for electricity generation. Of course, hydropower is much higher, 95%, but we are talking about different proposal, different technology. It has pros and cons, but we think that 61% is still interesting, and it's worth giving a shot to this technology. These are the road slope applied, that we combined the topography with the equation for estimating the road slope. This is the levelized cost varying with road slope. So at 15 degrees road slope, the electricity generation cost can go as low as $20 per megawatt hour. And here is the final results combining all the roads, all the infrastructure, and the costs. So in order to find the cost for electricity generation in different regions, you can see that the cheapest locations are mainly the Andes, the Himalayas, but there are a lot of other locations where this technology is viable and competitive, with wind power, with solar power, with even natural gas. And this is the other result, which shows the potential for electric truck hydropower. So also the highest potential is in the Andes and in the Himalayas. They have other mountain ranges also have significant potential for electric truck hydropower. And these are the cost curves. The cost potential curves. So it shows the potential and which is the cost. So the least cost with the potential. Of course, the higher the price, the more electricity generation you can generate. And there are very good opportunities with low cost, but then the low cost increases, and then the potential also increase. The continent with the highest potential is Asia, followed by South America, Central America, Europe, Africa, North America, and Australia. Comparing conventional hydropower with electric truck hydropower, we have, for example, the flexibility, location flexibility. Conventional hydropower is very low, is static. Electric truck hydropower is high, is mobile. Head flexibility, conventional hydropower is low because you have to design the plant to have inlet and outlet heads. And electric truck hydropower is very flexible because you can catch the water at different altitudes in the mountain. You can travel 3,000 kilometers altitude, 4,000 kilometers, 4,000 meters, altitude. Capacity factor, electric truck, conventional hydropower can be as high as 70-50%. Electric truck hydropower, on the other hand, is limited to, let's say, 35%, because the truck has to go up and down, and when it's going up, it's not generating electricity. Storage reservoirs, conventional hydropower allows storage reservoirs, which is good. Electric truck hydropower doesn't, so you can't store energy for the long term. Doesn't allow seasonal storage, for example. Conventional hydropower does. Applicability is usually applied in large rivers. Electric truck hydropower, small rivers, small stream catchment areas. Modularity, conventional hydropower is not modular. Electric truck hydropower is modular. Lifetime of conventional hydropower 40 to 100 years. Electric truck hydropower 3 to 10 years. Capex for conventional hydropower is $1,000 to $5,000 per kilowatt hour, per kilowatt of installed capacity. And electric truck hydropower is around $200 to $50 per per kilowatt hour. So the installed capacity is around 5 to 10 times smaller, but of course the OPEX is much higher. So the OPEX of conventional hydropower is low, electric truck hydropower is medium to high. It doesn't require fuel, so it's not like a natural gas power plant that you need to burn a fuel. That's why I said medium, because it just have high maintenance costs, but it doesn't require fuel. It just transports water from one place to another. So the levelized cost is estimated to be 50 to $200 for conventional hydropower, and for electric truck hydropower is 30 to $100. This cost is estimated with today's cost of electric trucks, assuming the truck from Alibaba that I showed you, and it assumes that the truck drives autonomously. There is no driver, so you don't need to pay a driver. It drives by itself, and the system is autonomous. To include in the discussion, you can use also electric truck hydropower instead of water, using ice. So you bring ice down the mountains, and then you can also provide cooling services for the bottom of the mountain. This is particularly interesting for India. And the conclusions are that electric truck hydropower is an innovative and flexible hydropower generation alternative. Levelized cost of electricity is around 30 to $100 per megawatt hour, which is cheaper than conventional hydropower, which is 50 to $200 per megawatt hour. The electricity generation global potential of the technology is estimated to be 1.2 pentawatts hour per year, which is equivalent to around 4% of the global energy consumption in 2019. Asia and South America have the highest potential of electric truck hydropower. Now, just give a brief summary of the media attention. So as I work for IASA does a press release for papers that they find interesting, and they did a press release on my paper, electric truck hydropower. And I was looking at Google Trends to show how many people looking for the word electric truck. And it turns out during the week that the press release was sent out, the searches for electric truck doubled. So you can clearly see that the press release had a huge impact, and a lot of people read about this. These are some examples in Twitter, for example, that was tweeted from different news sources that shared the paper talking about electric truck hydropower, and the altimetric results are until now 206, which is quite high. It doesn't fetch all the media outlets because I'm keeping track of all the websites. It's around 150 to 200 websites publishing the news today. Thanks so much for your time. I hope you enjoyed my presentation. I'm sorry not to be there to talk to you personally, but I'll be very happy to talk to you by email. So my email is there, Hunt@iasa.ac.at. Thank you so much. Have a nice conference. Bye-bye.